Okay, so rabbit population is given to us by that equation. Determine the intervals of time when the population is increasing and the intervals when it is decreasing. So I am going to be using the first and second derivative here. So let's start by calculating those guys. And then after you'll see why. Now this might not be the steps that you would have taken straight away, but you would have had to have done them eventually. So PT equals t squared ln 3t plus 6, where time has to be greater than 0. So time cannot be equal to 0 here. Okay, so first thing that we're going to do when we're calculating the derivative, we're going to look at it and acknowledge that it should be product rule. So p dash t, we're going to let u equal t squared, derivative of u be 2t, v equal ln 3t, and v dash equal, derivative of this will be 3 over 3t, which will simplify to 1 over t. Okay, so now I'm going to put it all together in my product rule. So t squared times 1 over t plus 2t times ln 3t. This one will cancel out with that one, and I'll just be left with the derivative being t plus 2t ln 3t. So that is our first derivative. Now we're going to find the second derivative. So to get the second derivative, I just derive the first statement, and I'm going to have to use product rule for that second part there. So u equals 2t, u dash equals 2, v equals ln 3t, and v dash equals 1 over t. Okay, and again, so the first part when I derive this is just going to become 1, plus now we're going to add on the answer to our product rule. So 2t times 1 over t plus 2 ln 3t. This is going to simplify. They will cancel out. Now I can group my like terms in the front there. 3 plus 2 ln 3t. And that is the second derivative. So I'm just going to highlight them quickly to make it easier for myself. So there's the first derivative. There's the second derivative. Now, if I want to find the areas where this thing is increasing and decreasing, first thing I'm going to do is I'm going to look for a stationary point. So remember, a stationary point is where the gradient equals 0. So it'll look like that, or it could look like this, or it could look like a stationary point of inflection. We just don't know yet. So exciting. So I'm going to let the first derivative equal 0. So our first derivative is going to equal 0, t plus 2t ln 3t. Okay, so first thing I'm going to do, move the t over. Now I'm going to take this across by dividing by 2t. T's will cancel out. I'm left with negative a half is equal to ln 3t. Take this over, it's going to become e to the power of a half. So e to the power of negative a half is equal to 3t. And then I'm going to take the 3 across by dividing. So I've got t is equal to this, or I could also say that t is equal to 1 over 3e to the power of a half. Now, the reason why I can do that is because if this has a negative indice, remember that means that it should be expressed underneath. They'll give you the same answers, just make sure that you know what you're doing. Okay, so now I found that my stationary point exists here. I'm going to use the second derivative test to test whether that point is a max or a minimum. Because really, with that stationary point, I've got most of my information. So I can test the stationary point. If it gives me inconclusive, then it's like this. If it gives me that it's going to be a positive number, positive in the second derivative test would indicate that it's at a minimum. So it's going decreasing and then increasing. A maximum would say that it's going to be increasing and then decreasing after that point. So very useful. Okay, so let's chuck it in. Okay, so we're putting it into our second derivative. So determine, we'll call it concavity. So 1 over 3e to the power of a half is equal to 3 plus 2 ln 3 times 3 plus 2. Wait, what am I even doing? Let me rub that out. In there is where I'm putting this answer, not whatever I had decided to do. 3e to the power of a half. Okay, so now we're going to start doing some fancy maths to flick this stuff around. So it'll still be 3 plus. Now this 3 can cancel out with that 3. So I'll have 2 ln. I'm going to convert this back to e to the power of negative a half here for a second. Now whenever you see this ln and then you've got e in here, that is going to cancel out and you're just left with whatever the power is. So that'll be equal to 3 plus 2 times negative a half. These will cancel out, you're left with negative 1, so it's equal to 2. So the second derivative test at that point gives you a positive answer. Therefore, it's a happy face. It's going to a minimum. Okay, so now we can start setting our domains. So at the very beginning of the question, you're told that t cannot be less than 0. So here in this section, we're going to say that for the values of 0 up to t up to 1 over 3e to the power of a half, it is going to be decreasing. And for when t is anything larger, then that should be the other way. Wait a minute. When t is anything larger than that, it's going to be increasing. Okay, so quickly let's just read through the question again to make sure that we've answered everything it's asking. So we're determining the intervals of time when the population is increasing and the intervals where it's decreasing. So we've done that here. Happy days. You do have another option as well. If you wanted to, you could pick a value in between. Instead of testing using the second derivative, you could test the nature around the point. So I could find my stationary point, and then I could substitute a value less than this and a value slightly more than this back in as t in the first derivative, and that would tell me the nature of what's happening around that point. But, potato, potato, this is faster.